Good morning, everybody, and today we are back with some more probability. Today we're going to be having a look at the variance, and we're going to be deriving the formula for the variance of a binomial probability distribution. So we have here our random variable x being this binomial probability distribution, and I have right here this little formula right here. This is actually the binomial probability formula. It gives you the probability that our random variable is equal to some value x right here. And strictly speaking, our x is actually always between 0 and n. Because if you have a look right here, we're only doing n trials right here. So it only makes sense that our x is somewhere in between that range. If we have 5 trials, for example, it doesn't really make sense for us to, say, for example, have 6 successes. So our x is always between 0 and 1. And today we want to find the variance of our binomial probability distribution right here. So how exactly can we get started? Well, first of all, why not just use the definition of the variance? What is the definition? It's exactly the sum running through all the x's, and we'll figure out the values of x later on. Actually, why not do it now? Our x is between 0 and n, so if we're going through all the x's, we're going to go from 0 all the way up to n like so. And what else do we have in this sum? We're going to have x minus mu. This gives us the distance our point x right here is away from the mean, and then we're going to square that because we want a positive number, and then we're going to multiply that by the probability of that particular value of x. So this is the definition of the variance right here, and we can actually transform this definition a little bit, because notice we have some kinds of function of x times the probability of that particular value of x. So we can actually rewrite this thing as being the expected value of this function right here. So we're going to have inside big X, because we're going back to our random variable, so big X minus mu, all squared, and then close that off. And you can check for yourself, but if you use the definition of the expected value, you're actually going to get back to this expression right here. So this relationship holds, and now what exactly can we do? Now it's just a matter of actually just playing around with this thing right here. So if we expand out this binomial thing right here, we're going to have the expected value of, first of all, capital X squared minus 2 x times mu plus mu squared. And then now to calculate the expected value of this, we just need to expand out this whole thing, because we can use the linearity of the expected value to break everything apart, kind of. So this is going to result in the expected value of, first of all, this part, which is x squared, and then we're going to have minus, and now we can actually bring this 2 and this mu out to the outside of the expected value, because it's just a constant. So we're going to have minus 2 mu times the expected value of x, and then we're going to have a plus mu squared, because mu squared is just a constant, of the expected value of, well, just 1. And the expected value of 1 is just 1, because 1 is really just any other constant. This thing's going to vanish, and then notice right here, we have 2 times mu times the expected value of x. But the thing is, mu and the expected value is the exact same thing. So I can actually rewrite this thing a little bit. This is exactly equal to e of x squared minus, and then we're going to have 2, and then we're going to have e of x squared, actually e of x, but the whole thing squared. I'm going to write it like this, e squared of x, plus, and then this thing right here, mu squared, is exactly the same thing, e squared of x, and we can clean up this part a little bit. Minus 2 plus 1, that's exactly minus 1. So we can rewrite this in the end as being e squared of x like so. So what have we found right here? We've found a relationship between the expected value and the variance. We showed that the variance of our x is equal to this thing. And this is actually quite a nice result, because we can use this now. So let's see, I'm going to rub out all of this because you don't really need it anymore. We just found out that the variance of our x is equal to e of x squared minus e squared of x, like so. So right now you might be tempted to just plug the definition of the binomial probability thing into this formula right here, but things actually won't work out too great. Mostly because of this x squared right here. So we need to kind of transform this x squared a little bit because it's just going to make our equations a little bit nicer. So if we take a look at the expected value of x squared, it would actually be nice if we can subtract off the expected value of x, because in doing so, if we combine these two expected values, we're going to get the expected value of x squared minus x. And we can factor this out a little bit, and this is going to give us the expected value of x times x minus 1, like so. And this thing right here is actually a lot more nicer to work with than the expected value of x squared. But the thing is, this has an extra negative e of x, and we don't really want that. So in order to kind of compensate for that, we only want e of x squared. We must add the expected value of x on both sides. So if we add this on both sides, and I'm actually going to write this thing right here, the expected value of x, as just mu, just to simplify things a little bit. So yeah, these two are going to cancel out. So negative e plus e. And we just found an alternate expression for e of x squared. It's just going to be e of x times x minus 1 plus mu, like so. Alright, and now we can actually plug this right into here. So now we're going to have the variance of x being equal to, so this thing is now equal to e of x squared, but we just found that it's equal to the expected value of x times x minus 1 plus mu. And then notice we have this negative e of e squared of x right here. And we can actually rewrite this as just mu squared. So this is going to be minus mu squared, like so. Alright, very nice. So we found that the variance of x is equal to this thing right here. We've kind of transformed things a bit nicely. And now all that's really left to do is calculate this thing right here. That's going to take up the bulk of the video, I guess. So calculating the expected value of x times x minus 1 isn't too bad, I guess. It's better than calculating the expected value of x squared. So to calculate that thing, let's just plug the probability formula into that equation. So on the right hand side of the board right here, we're going to be solving the expected value of x times x minus 1. Alright, let's actually just use the definition of the expected value. This is going to result us in the sum running from x equals 0 to n, because remember our x is always between 0 and n, of, well, we're going to have this function right here, so we're going to have x times x minus 1, like so, and then we're going to multiply that by the probability of that particular value of x. That's just plugging in the definition of the expected value. And remember, the probability of x is equal to this very thing right here. So if we substitute all of that stuff in, we're going to have now the sum running from x equals 0 to n of x times x minus 1 times the probability of that particular value of x. That's just going to be n choose x times p to the x times 1 minus p to the n minus x, like so. Now I have to play around with this thing a little bit. I'm going to do a couple of simplifications first of all, because notice this first part right here. When we plug 0 into here, we're going to kill the whole thing, because this x right here is going to turn to 0. And if we plug x equals to 1 into here, into this expression, this factor right here will turn into 0, because 1 minus 1 is 0, and it's just going to kill off the whole thing. So technically, we can actually start the sum at 2, because if we start the sum at 0, then the first two terms of the sum right here will actually be 0. So we can start the thing at 2, and everything will still be the same. So where can we go after this right here? I'm going to expand out this n choose x right here. Just plug in the definition. So n choose x, what exactly is that? That's just n factorial over x factorial times n minus x, but the whole thing factorial. Alright, and now I want to take a look at a little bit of factorial stuff, because if you look at this part right here, x factorial, and we have this x times x minus 1. This part right here looks like a truncated factorial kind of, and we can actually simplify that thing quite nicely, because x factorial, that's exactly equal to x times x minus 1 times x minus 2 times dot 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 times 2 times 1, like so. And we have this x minus 1 part right here. So x factorial you can actually rewrite this as being x times x minus 1. And then if we start at x minus 2, we're still going to have products of everything downwards, down to 1. So we can actually say this is x minus 2 factorial. So this whole thing right here, down to 1, is x minus 2 factorial. And if we sub this definition of x factorial into here, this x and this x minus 1 will cancel out with the x and x minus 1 right here. So what we can actually rewrite this as is the sum running from x equals 2 to n of n factorial over, and now this x factorial right here, these two factors will actually cancel out, leaving us with x minus 2 factorial. So we're going to have x minus 2 factorial times n minus x factorial, and then we still have p to the x and 1 minus p to the n minus x, like so. Now I want to simplify this thing a little bit further. Notice that we have an x minus 2 right here. We can't really do anything about that. So why not actually change all the x's to x minus 2 somehow? And how can we do that? Let's start off with n minus x right here. We have n minus x. Let's actually just go about this part right here. We have n minus x, and ideally we would like an x minus 2 right here. So ideally we want this. But notice that this thing right here, that's exactly equal to n minus x, double negative, so plus 2. We're off by this addition of 2. So in order to return with a n minus x, we need to subtract 2 on both sides. So if we do that, subtract 2 on both sides, this positive and negative 2 will cancel out, leaving us with, now we have this expression right here. Let's just rearrange this a little bit. This is n minus 2, and then we're going to have minus x minus 2, like so. And this thing right here is still equal to n minus x. And the nice thing is we have this x minus 2 part right here that we really want. And we've also generated an n minus 2 in the process as well. So if we actually substitute this thing in for this part and this part, we're going to get the sum running from x equals 2 to n of n factorial over x minus 2 factorial, and n minus x will turn into that expression right there. So we're going to have n minus 2 minus x minus 2, whole thing factorial. And then let's actually muck around with this p to the x while we're at it. We want an x minus 2 right here, so we're going to have p of x minus 2. We can't just subtract off the 2, we have to add it 2 again because we want to make everything equal. And this plus 2 right here, we can rewrite this as a multiplication by p squared. And that p squared, let's just bring that up to the front somewhere because that's actually just a constant in terms of the sum right here, which is in terms of x. So this is p squared times this whole sum right here. Alright, we have this part sorted out as well, which is nice. And then we have 1 minus p times, let's see, n minus x is exactly that thing I showed right there. So we're going to have n minus 2 minus x minus 2, like so. Alright, we've made things a lot more messier, but that's actually a good thing because we can simplify things quite nicely later on actually. All that's really left for us to do is to transform this n factorial, because now notice how we have n minus 2's everywhere. Ideally we want this n factorial to become n minus 2 as well. But remember from that factorial thing I showed before, we can rewrite this as being n times n minus 1 times n minus 2 factorial. That whole thing is still n factorial. And we've generated an n minus 2, so let's actually rewrite this whole entire thing. Let's bring up this n times n minus 1 because it's just a constant. So we're going to have p squared times n minus 1. And then we're going to have the sum running from x equals 2 all the way up to n of n minus 2 factorial over x minus 2 factorial, x minus 2 minus n minus 2, actually n minus 2 minus x minus 2, sorry about that. So minus x minus 2 right here, so much writing. And then we're going to have p to the x minus 2, 1 minus p to the n minus 2, minus x minus 2, I'll put it like that. So this is a lot of writing, hopefully you guys can see it all, but now we can go on and do our substitution, because our substitution will make things a lot more nicer actually. So notice we have x minus 2 and n minus 2's everywhere. Let's first of all substitute the x's. So if we let, for example, if we let some new variable z be equal to x minus 2, then we're going to transform all these x minus 2's into z. So this is going to turn into a z. This is going to turn into a z right here. X minus 2 up here will turn into a z. And this x minus 2 will turn into a negative z, which is quite nice. And notice our index right here as well, because our index is in terms of x, but we've shifted our index a little bit. So when x is equal to 2, if we sub 2 into here, our z will actually start at 0. So if we change the index, our z is going to start at 0. And if we plug our upper bound, n, into here, we're going to get n minus 2. So our z is going to end at n minus 2. Okay, we've generated another n minus 2, isn't that quite nice? And now let's substitute all the n minus 2. So if we let some new variable m be equal to n minus 2, let's actually I'm not going to rewrite this whole thing, I'm too lazy. This n minus 2 right here, that's going to turn into an m. And then this is going to turn into an m. What else is going to turn into an m? This is going to turn into an m. This is going to turn into an m like so. And we are left with this thing right here. That's a nice simplification. We've gotten rid of a lot of junk. And now let's actually start cleaning things up a little bit. Let's take a look at this part right here first of all. M factorial over z factorial times m minus z all factorial. That's pretty much m choose z. That's the definition of m choose z. So let's do a replacement right there. So this thing right here is now equal to m choose z like so. And what else can we do? I think that's all we can do really. Let's rewrite this a little bit. So this is now equal to p squared times n minus 1 times n. I don't know, I wrote that the other way around. Of the sum running from z equals 0 to m of m choose z of p to the z times 1 minus p to the m minus z like so. And this inside of the sum right here, that's basically this formula for the binomial probability, except we have m's and z's, but the variable really doesn't quite matter. So this whole inside right here, we can just replace it with p, the probability that our x is equal to some value x. So this is now equal to the sum of the probability that our x is equal to x, or if you want just p of x. And what exactly is the sum right here? Well, we're summing up all the probabilities. Let's just change the index a little bit here just to make things a bit nicer. So this is the same as going from x equals 0 all the way up to n. And well, this thing right here, if we're summing up all the possible probabilities of our x right here, that's just going to give us 1. The sum of all the probabilities is exactly 1. So what are we left with? We're left with the expected value of x times x minus 1 being equal to just p squared times n minus 1. So that's quite nice. So now what do we find out in here? We found out that the expected value of x times x minus 1, this is going to result us in n times p squared times n minus 1. Yeah, it should be right. So np squared times n minus 1. And how about this plus root negative mu squared right here? Well, I've derived this in a previous video, the expected value of a binomial probability distribution, some video like that. But the expected value of a binomial probability distribution is just n times p. So that's mu right there, and then we have negative mu squared, which is just n times p, but the whole thing squared. And we can leave it like that if we want to, but we can actually simplify things a bit further. If we expand out this bracket, we're going to get n squared times p squared, negative 1, so we're going to have minus np squared like so. And then we're going to have, plus n times p minus, let's expand out this thing right here, so negative n squared times p squared like so. And nice thing is this negative n squared p squared and this positive n squared p squared, those will actually cancel each other out, leaving us with n times p minus n times p squared. And we can factor this out a little bit more. This is equal to, we have a common factor of n times p. So this is going to be n times p. And then we have one of those minus another p. So 1 minus p. So overall, what exactly did we just find right here? We found in the end that the expected value of a binomial probability distribution thing is equal to, did I say variance? Yeah, the variance of a binomial probability distribution is just n times p times 1 minus p. That's really quite nice. And from here you can just directly find the standard deviation of such a distribution just by taking the square root. So if we want the standard deviation of our x right here, that's equal to the square root of n times p times 1 minus p, like so. And notice we have this np right here. That's exactly the mean. So if you want, you can actually just write this as the expected value of x times 1 minus p, or just mu times 1 minus p if you want to. It's really the same thing. But yeah, those are the two results, I guess, that we've derived today. That was a lot of work for just these two things right here, but yeah, that is quite nice. It's interesting to know the derivation behind all of this and everything else. So yeah, that is pretty much it for this video. I hope you guys enjoyed it. If you did, make sure to subscribe, like, comment, do whatever you want. But yeah, up until next time, have a wonderful day, and I'll see everyone later. Bye bye.